I thought that we wrote down that OCH2CH3 is a big bulky base and can't do an SN2 reaction, but we saw that it did.
Yeah, it's actually not that bulky, so
Because I wrote it,
let's review that.
and I remember writing it on here, so.
So is this a strong base?
Yeah.
Yeah, if you look at your handout, you'll see that oxygens with negative charges are strong bases. So this is a strong base.
Oh, that has nothing to do with the fact that it's a hydroxide?
No. So whether it's strong or not is just the fact that it's an oxygen with a negative charge.
Okay.
If you take a look at the handout here, oxygen with negative charge would give you a strong base. We also see that here, oxygen with negative charge would give you a strong base. So that means it's good enough for E2. This could do an E2. Now, does this look bulky or not?
No.
Yes, it's pretty obvious, non-bulky. So would we usually get E2 or SN2 here?
SN2.
Yeah, usually SN2. All right, now we could say put in this. All right, this is still strong. It's bulkier, but it's still not very bulky. I would still call this non-bulky. So still usually SN2. And pretty much we could call this a primary oxide, because this carbon is primary, so primary oxide. So pretty much any primary oxide is not too bulky.
Oh, it doesn't matter how long the chain is, that's all that makes it bulky.
That's right, because remember, what really matters is things that get in front of the oxygen. But once you get out here, this is so far away, it's usually not going to bend around to block the oxygen. Okay, now, how would we analyze this? Is this still a strong base? Yes, because it's still O minus. And I hope this looks pretty bulky. Yeah, this is about as bulky as we get. This is a strong, bulky base. This is so common, you should probably know the name of this. This is tert butyl oxide. Have you heard this talked about in class? All right, so this is tert butyl oxide. Tert butyl oxide. Strong, bulky base. So is this going to favor E2 or SN2?
E2.
Because what's the big obstacle to SN2? Steric hindrance that blocks the nucleophile. Well, this has too much steric hindrance. So this could almost never do an SN2 reaction. It's pretty much impossible for this to do SN2. It's almost always going to be an E2 reaction over here. All right, so I don't think on the exam they're going to give you very close calls. It's going to be pretty clear whether things are in this category or this category. These should be a good enough dividing line between a bulky and a non-bulky base. Have you guys heard LDA discussed?
Yeah.
No.
All right. Yes? No?
I haven't.
All right. Well, if any of you have heard of it, you probably should know about it. So LDA.
The dog. Nope.
All right. So the L stands for lithium. The D stands for diisopropyl. These are two isopropyl groups. And the A stands for amide. Probably don't need to know what it stands for. You should just know LDA. Does this look bulky?
Yeah.
Yes.
Yeah, these isopropyl groups are great big, they're like great big windmill blades that are constantly whirling around and getting in the way and causing steric hindrance over here. So this would also go in the category of a strong, bulky base. So what type of mechanism would we expect here?
E2.
Yeah, pretty much always. Almost always these will give you E2. And actually on the exam, most instructors don't make this too close of a call. Usually if they use a bulky base, it's E2. And these are almost all, well, I don't know, most instructors, these are the only bulky bases they tend to use. These are by far the most common bulky bases. And if you see these, you pretty much know it's going to be an E2 reaction. Let's take a look at that in the handouts, page 3. So we can see at the bottom of page 3 that O minus is a strong base, but it could either be in a bulky base or a non-bulky, and the two common bulky bases are LDA and tert butyl oxides. That's in the bottom of the handout. LDA and tert butyl oxide are the common bulky bases, and you can see those almost always give you E2.
So, and anyway, no matter what, if it's hindered, it'll be E2.
Yeah, so why are these E2? Because, so in the right-hand column, we're getting E2 because of steric hindrance from the base. Right? In this right-hand column, we're getting E2 because of steric hindrance from the base. But we also get a lot of E2 even outside of that column when we're in the lower rows. Why do we get E2 in the lower rows? Because now we're getting steric hindrance from the substrate. So to the right in that table, you have E2 because you're getting steric hindrance from the bulky base. And in the bottom rows of the table, you're getting E2 because you're getting steric hindrance from the substrate. So if you're getting steric hindrance from either of those, that's going to give you E2 and not SN2. So by the way, notice that we've kind of been assuming that steric hindrance is not an obstacle to E2. All right, and that is the case. In fact, there really isn't any big obstacle to E2. So E2 basically happens unless somebody else gets in first.
Okay.
So if SN2 is not, so we can use the big obstacle to SN2 and SN1 to decide whether SN2 and SN1 are good ideas, but there's no particular obstacle to an E2 reaction. Notice that E2 can happen with any substrate, primary, secondary, or tertiary, because as I just said, steric hindrance is not an obstacle to E2.
So what's the most preferable is SN2. But if you can't do SN2, then SN1. If you can't do that, E1. Then if you can't do that, E2.
Yeah, maybe what I said kind of sounded like that, but I shouldn't have said that. Yeah, I guess we can't really say that anybody's the default. You really have to use the table and get practice. There isn't any one default. All I wanted to say is that we don't really have any big obstacle to focus on for E2, like we do for SN2
Just
and SN1.
if there are obstacles that get in the way of SN1 and
SN2, then there's a good chance it would be E2. But remember, it's always possible there's no reaction. So it's really always important just to kind of look at all the factors in the table.